Hello everyone, John Vincent back here with you, and in this session we're going to talk about NX-CAM 5-axis techniques and some of the new functionality and features within these latest two versions, NX 2007 and NX 2206. Some of the contents. We're going to look at geometry setup. This is going to look at part workpiece specifications, blank specifications, MCSs, things of that nature, specifically tied to 5-axis equipment. We're going to look at area milling and how we can control the point distribution with the max cut setting that's now available in the area mill operation, and use it with the tilt tool axis to give us some nice surface finishes in multi-axis operations. And then lastly, we'll take a look at merged path in conjunction with some contour profile operations. Alright, so the first thing I'm going to take a look at here is our geometry setup. I get asked time to time, what's the right way to set up my geometry structure? Should I have an MCS with a workpiece attached to it? Maybe a workpiece with an MCS attached to it? What's the right way of doing things? And the answer is it depends. It depends on what type of machine you're working with. It depends on your post-processor requirements. Depends if you're using NC simulation and what types of auxiliary functionality are we trying to simulate. Things like tail stocks or steady rests, other kind of supports, things like that. So we'll touch a little bit on some of these items right now. I'm going to go ahead and jump over into NX, and we'll take a look at a simple example here. And if I go to the geometry view, we can just take a quick review of this current part's structure. And again, we want to talk about two topics, MCSs and part geometry. So just looking as we go down this process, we have our main MCS, and that's in this particular case specified right at the bottom of our part. We have a workpiece that's called blank, so we're only specifying our blank geometry at this level. We then have a local MCS specified at the top of our part, followed by the actual part geometry itself. So let's talk about the workpiece first. In this example, I have a variable contour operation, and this is something I have done from time to time, and I don't want any part geometry or cut area to be specified in the operation. You can see when I open up the operation, I have neither part geometry specified or cut area specified. What I do have is some auxiliary geometry that I created just by offsetting between these opposing walls. So then essentially I have a face, this face geometry running right down the center of my part. And in this example, I'm using that as my drive geometry. And I've specified the tool position to on to have a nice helical cut pattern going down in a 4-axis type motion, essentially just slotting out this part geometry. So that's one use case, just the ability to not have part geometry and cut area specified. However, I can still inherit my blank geometry, and my IPW will update properly on down the line. That would not happen if I had my blank specified at this part level. I would not be able to have my IPW available to me at any time if I wanted to just review this individual operation. So that explains kind of the reasoning why I like to divide those two up. I don't always use that, but it's nice to have that built into my template for when the time is right. Now the next portion is to look at, in this case, I have a main MCS specified at the bottom of my part. And typically what I'll do, again, this goes back to your post-development and some other things, but on a 5-axis machine, I'll set up my main MCS, and I'll specify it as fixture offset 0. This is essentially specifying my G53 location, my home position on my particular machine tool. This allows me to program off of a known location if necessary. Say I don't have any coordinate systems set on my machine tool. I know, for instance, on a particular machine, my XYZ0 is right at the center of the table and the face of the table. So I can mount a part on a vise, in a chuck, or whatever the situation might be, and as long as I'm reasonably close, I could go ahead and do some probing operations, for example, and probe my XY center, Z0 face, and use that to set my work offset. So that work offset that I would be setting would then be my local MCS. And this would be using my fixture offset for G54, G55, so on and so forth. And this is then a local MCS where I'm just specifying that this is my actual fixture offset. And this is where all my code is going to be driven from. Additionally, you can do some other things. So in this case, I have, if we look at a Heidenhain post-processor, I have this variable contour operation attached to my local MCS. That's the top of my part. When I go ahead and post this code out, we'll see that we're actually going to get a function in the post that's going to run on the machine, cycle def7. And this is going to do a local shift for this particular operation. So I'm shifting from my MCS main, which is the bottom of my part in this case. I'm shifting my work coordinate here on the fly in the program to the top of my part. And you'll see that all of our coordinates are going to be updated based on this. In this case, let's look at this first Z value, negative 1.6 and change there. Well, let's go ahead and cancel this. And then move my variable contour operation so it's no longer a child of my local MCS. And when I post this out again, we'll see that that cycle def7 is no longer in the code, so we're not doing any kind of shift in the program. But the actual output, all the positions are changing. So it's compensating in the code versus just doing a local shift. Number of use cases here. It doesn't have to only be a Heidenhain machine. It could be a number of other things. For instance, we could look at, on a FANUC machine, G68.2, typically where you do our plane rotation about our work coordinate. So wherever our G54 location is, we do the calculations in the control when we command a G68.2, X0, Y0, Z0, and then the angles that we're positioning to. By the same token, you could be working on a prismatic part and have some local shifts, and this will enable the code to be a little bit easier to read. So if I had some geometry on a side of my part, I could offset kind of locally to the center of a face or a center of a board feature that maybe things are dimensioned off of, generate my code. The G68.2 would offset to that location along with the rotary changes, and then my code would be based off of that local shift. So different strategies. You have the ability to operate the way you want here inside of NX. Moving on to the next topic, we'll start taking a look at area mill operation. And really the big enhancement here is that we now have the ability to set our cut step with the max step option. When we go back into NX and take a look at this part file, we can see this is a large part, very open, free-flowing surface. If I turn on my endpoint display on my toolpath, what we can see is we have some very long segments here. And really, all the point distribution is purely driven from our in and out tolerances in the software. If we want to tighten these up and make our point distribution a little bit more fine and a little bit to let our control have more data to read, apply whether you have Heidenhain, FANUC, Siemens, apply their own smoothing functionalities, tuning parameters, things like that. We can specify a max cut step value, and when we generate the toolpath, we'll see we have a lot more data here. We have a lot more line segments. It's going to be a lot more code, so you have to have the right controls, machine tools to handle this information, but you're going to have a result of a higher quality toolpath. So let's take a look at how do we apply this in a multi-axis application now. In this case, we have a toolpath. I'm going to turn off those endpoints here, easier to see. We have an area mill toolpath, and we see that there's a couple uncut regions. These regions are uncut because of the collision check. We're checking for our tool and holder geometry against our part. And in this case, we would have some collisions by cutting those areas. Well, I want to ignore that setting. I want to go ahead and generate a toolpath all the way throughout that region, even though in this particular scenario, our holder is going to gouge the part. But I'm going to use the functionality tilt tool axis to clear our holder from the part geometry after the fact, after the actual toolpath has been generated. So essentially we're going to be transforming this from a 3-axis toolpath into a 5-axis toolpath. So we'll see here, once the toolpath generation is complete, we'll be able to go ahead and go to the next step, which is going to be tilting this tool axis and providing the clearance we need for this particular operation. Alright, now that we have our toolpath generated, we can take a quick look at this, and we can see that if we come into some of these different areas, let me come down into this pocket, we have some areas where we're definitely going to be colliding with our part geometry. I could run a gouge check and see this as well. But what we want to do is apply this tilting. So we come to our toolpath option, tilt tool axis, and in here you can specify a little bit of machine information. What is your main MCS axis? What are some limits to your machine? What are some clearances we want to maintain? And by specifying these settings and saying OK, NX will go ahead and kind of recalculate the toolpath. It'll modify the toolpath, essentially just tilting the tool away from the part geometry to maintain any clearance values you set in that tilt tool axis function. So any regions that were colliding with the part or violating our clearance region, they're now going to be tilted away in a 5-axis motion. Alright, and here our tilt tool axis process is wrapping up, and we'll be able to go ahead and verify that when we go and play this, we'll see that right away we get some tilt, some rotary engagements on our part. So we're not going to be gouging or colliding with our part geometry at all. So that's one option for using tilt tool axis. But maybe you don't want it to be applied to your whole part. Maybe you only want it to be a portion of your toolpath. So there's a couple other things we can do here. And in this case, let me go back to that cylinder head. Again, here we have, with our cut regions ignored, I'm going to go ahead and actually generate or create these cut regions now. Come to geometry, and to my optional geometry under cut regions, we can see that I can choose the option create region list. This is going to go ahead and create all the individual regions in a list, and this is essentially what NX is doing behind the scenes with the check for collisions, and it's just suppressing the regions that we have collisions occurring and ignoring those regions, and they're not going to be used. So we're essentially doing the same thing here. Let's just let the region list finish being created. And sure enough, here we can see that certain areas don't have a check mark next to them. Those are the ones where there was some collisions happening. Here we can see our collision reports. So with that, we'll say OK. Okay, we do have to generate our toolpath again. So I could create a new operation, or I'll just go ahead and copy this one and paste it. And now we would have the ability to go ahead and import our existing region. So let's go ahead and create that region list. And now we can focus just on those particular regions. So here, maybe we would want to use our tilt tool axis. Maybe we'd go back and just use a longer tool in this particular operation. Whatever your preference is for your process. And you can see we're focusing just on those uncut regions now. Okay. And now looking at contour profile and merged path, we're going to be looking at how we can program contour profile, getting into a little bit more of the settings inside of contour profile, maybe some users are not aware of, and then we're going to merge multiple regions together to change the non-cutting motions between these multiple regions. So here we have an example. This was similar geometry to a customer's issue. And we have some different, I think it kind of lends itself to a unique scenario here. In this operation, we really want to cut the two blend radiuses on either side of this feature, and this face with the kind of this reverse draft to it. So I'm going to go ahead and create a contour profile operation. And here's my contour profile. We'll use a little 1/8 inch end mill, and we'll say OK. So now for this specific requirement, we need to specify our wall geometry. We don't have any floor that we're going to be driving on, but we don't want to start directly in this radius. We want to start a little bit before it. So I'm going to select these faces that come a little bit past the actual geometry that we're focusing on. And maybe I'll set my tool axis vector here. Oh, we got rotated around there a little bit. Let's come back here into my operation. And I'm going to set my tool axis vector. I'll come in to specify this. I'll just use my view direction for right now. That'll be fine. And we can see if I generate this, first I'm going to turn on my follow wall bottom. I'll put a little offset in there, 2mm offset. And I'll be able to generate. And we're going to get a toolpath, but it's not really what we want right now. In this case, we're going to NX is trying to cut as much as it can. We don't really want it to cut this wall. Maybe just start a little bit before we get into this blend. So here's how I would like to handle this. Inside of the strategy page, I'm going to manually select my start points and end points, and I'm going to use a guided tool axis. So to do this, I'm going to go ahead and just pick, in this case, I am using this intersecting point of this existing geometry as my point. I'm going to specify my tool axis as guided as well, and I'm selecting the edge of this blend to guide my tool axis, and I'm going to make very similar selections on the opposing side. So we'll come and specify our point. Inferred point is already on here. Let's go ahead and make that selection and guide our tool axis. And now when we generate this tool path, we'll see it's really doing what we want. We're going to engage before the blend itself, then feed in there and around this geometry. This was a hard material. This was a titanium. So I'm going to add a couple extra passes in here. So first thing I'm going to do, change my engage motions a little bit. Turn off the automatic override with smooth connections. And I'm simply going to engage from a point. And additionally, I'm going to add some multiple passes. And I think we have, I'll do side passes. Got about 1 millimeter of material. I'll say 5 passes. And we can go ahead and generate this. Alright, so we have our toolpath we want. We're engaging nicely. Now we want to do this for all 4 regions. So I know that this is axis symmetrical here. So let's go ahead and just transform this toolpath right now. Specify a point and a vector. Yep, we're going to instance it, 3 instances here. Alright, we have all of our toolpaths we want. And now for using the merge toolpath option, I'm going to insert a new program group. And an option we have, this is only for multi-axis operations, is the merged path option. I'll just say OK, and I'm going to place all of these operations inside of this merged path group. And what I want to do is have non-cutting motions connect all of these regions. So I'm going to edit my merged path, and I'm going to edit my non-cutting moves. And here I can change up some of my clearance settings, smoothing options, things like that. So I'm going to use a cylinder, kind of make some similar picks here to choose my orientation of a bounding cylinder. I think I can use 30 millimeters for a radius. Yep, that's plenty of clearance. Smoothing, I could come in if I wanted smooth corners, all that kind of stuff. I'll turn those off. And we can go ahead and generate this. So it doesn't actually generate the toolpaths, it just generates applying non-cutting motions between these operations. Now this is kind of cool, especially if you build in logic into your post-processor in start of path, end events, end of path events, to do things like send the machine tool home or clearance to Z, Z homing or things like that. A little bit more efficient toolpath. Kind of a cool thing that's been out just for the last couple of releases now. So something worthwhile looking into. Alright, so I hope you found some of this information beneficial today, and that you'll be able to utilize some of these tips and tricks in your day-to-day programming. If you do have any questions, comments, feel free to reach out to me anytime. Again, my name is John Vincent with Swoosh Technologies. Take care.